Welcome to Basics of Noise and its Measurement. This week we have been discussing discrete Fourier transform, and what we will do today is continue that discussion further. Till so far what we have learnt is how to use the DFT method to compute frequency spectrum of a discrete time signal. What we will do today is a couple of things, but first thing we will discuss is that what happens to our solutions or the frequency representation if the duration of the time changes. So how does the goodness of my results get influenced by the duration of the time signal. Second is how does sampling frequency affect the accuracy, and the third thing is what is the resolution of my solution or the frequency representation, and how does it get influenced by different parameters. So that's what we are going to discuss today. So duration, the influence of duration, sampling frequency, and how does resolution get influenced by various parameters which go into discrete Fourier transform of a time series signal. So the first parameter we will look at is why importance of duration. So what we will do is we will look at we will first generate a time series signal, and we will generate it for different durations. And then what we have done is we have taken its Fourier transform, discrete Fourier transform, using some industry standard tools, and we will look at those solutions and see what we make out of that. So the function we will use is this thing, y equals 2 of sine 2 pi ft, okay, and f we set it at 1 hertz, and the sampling frequency was not changing, and we were doing 16 samples each second. So sampling frequency was 16 hertz. So let's look at some of the results. Okay. So this is the signal. This is the time signal on the left, and this is the function 2 sine 2 pi ft, f is 1 hertz, and I ran this for, it says 0.3 seconds, but I actually ran it for a little over 0.18 seconds. So I had 1, 2, 3, 4 samples. Okay. So this should not be 0.3 seconds, it's different. It was about 0.19 seconds, and I got 4 points. So I have 4 points of this signal, 1 hertz signal, and then I did an FFT. And what I see is that I get at 0 hertz, I get a peak, and the amplitude is slightly over 2, and then I get another peak at another non-zero value at 4 hertz, and all other values I got as 0. Okay. So I got these two values, 0 and 4. And if you look at the accuracy of this result, it is totally wrong. Okay. So what that tells me is, see, my sampling frequency was 16 hertz, it was fairly high, so I should be able to capture 1 hertz tone. So there is no problem with sampling frequency. So what else is the problem? Maybe the duration, maybe I put the duration too short, because those are the only 2 parameters. If I have, this is my raw data, and if I am not getting correct answer, maybe the signal is too short. Okay. So then I said, okay, what I will do is I increase the signal length, and again this says duration is 0.6 seconds, it should have been 0.5 seconds, and over 0.5 seconds I have this type of a shape. I have this type of a shape. And then I again do the FFT of this or DFT of this signal, and what I get is, so here I had 2 points, Now I have 1, 2, 3, 4 points. I have a peak at 0 hertz, another peak at 1.5 hertz or maybe 1.7 hertz, another peak at maybe 3.6 hertz, another peak at a little over 5 hertz. The real solution should have been all these values should be actually 0, and I should have had only one peak at 1 hertz and its value should have been 2. So what this means is that this signal is still too short. So then I increase the signal to little over, slightly less than 1 second, and I have 16 points. I have 16 points. And if you take this signal and you cut and paste it again, it's a repeating signal. So I have 16 points, and sampling frequency I still has is 16 hertz. So I have not changed this sampling frequency over this entire analysis, and what I get is a perfect result. All values are 0 except at 1 hertz, and the value of at 1 hertz is indeed 2, which is the actual case. Okay. So first thing what this tells me is that if I have a complete sinusoidal cycle and if I take its FFT, I will get the right results. But in real signals, we do not know whether we have complete sinusoidal cycle or not, because we do not know what frequencies are. Okay. So then what happens? So we have to have fairly large duration. We have to have fairly large duration. So this is T is, again I deliberately put it as 1.7. Again, I don't know why these numbers are incorrect. So I deliberately put it at 1 second so that it is not a complete cycle. And if it's not a complete cycle, but it's 1 hertz is one complete cycle, and this is maybe 1.7 cycles long. And when you do in FFT, you get somewhat moderately or semi-moderately good results. What you see indeed is that there is a peak at maybe not 1 exactly, but 1.1 hertz, and all other values here in excess of 4 hertz are very small, but you still have appreciable values at 0 and maybe 0.7 hertz and maybe 1.7 hertz, and these. So these may be very small, but I can certainly not ignore these 4, 5 values. But this value is pretty high, 1.8. It's getting close to 2, but it's still not there. So what is happening is that the energy at 2 hertz, it is getting distributed around 2 hertz. Energy at 1 hertz, which is reflected by its amplitude 2, it's getting distributed around 1 hertz. So that is what is happening. So what that tells me is that this not 8 but 1.7 second is still not probably the right duration. So again I make it 2 seconds. 2 is, I have exactly 32 points. 16 hertz is the sampling frequency. If you count the number of points, it's 32. And when you do this, you get a perfect result again, because your cycle is, if I just again take this thing and paste it here, I have a complete cycle. Okay. So once again it reinforces, if I have a complete repeating pattern, then I will get good results, but we do not know whether our repeating pattern. So I have to increase the, so this is 2.3, and you see that compared to that 1.7, it's not significantly different, but it may have slightly improved. 4 will again, as expected, it will give good results. So what this shows is that you have to have a fairly large, maybe what we should have done in this is that we could have taken maybe 5, much longer duration, maybe 5.5 or 6.8 seconds. And what you would have seen is that when the duration becomes long, then this value gets better and better. So that is the first moral of the story, that your duration should be reasonably long. And it is also related to another factor, that the number of points which you are sampling, it should be ideally a power of 2, because that also helps you get good results. So maybe we will do that numerical experiment and show the results in the next class, but that is another thing. So this is one. The second experiment or the second study which we are going to talk about is about the importance of sampling frequency. So in the first case it was importance of duration. The second is about importance of sampling frequency. So what we have done is constructed a signal y equals a n sine 2 pi f n t, and n is, so basically we have generated 6 sine waves, a1 sine 2 pi f1 t, a2 sine 2 pi f2 t, so on and so forth. And these 6 sine waves are such that the amplitude of first sine wave is 1, second is 2, third is 1.45, fourth is 3.5, and so on and so forth. And the frequencies of first wave is 1, 3, 10, 16, 17 and 28. So we have just picked up some numbers. And if you look at our results, okay, so this is our waveform, and the overall duration of the signal is slightly less than 3 seconds. So it's not exactly sitting on this vertical line, slightly less than, but you have a lot of points. Okay, you have a lot of points, and the number of points, it is 32 times 3, because this duration is 3 seconds. So it will be what, 96 points. It will be 96 points. And when I look at the DFT of this, my values are somewhat okay. At 1 hertz, so this is 1, my amplitude should be 1, and it is indeed 1. At 2, no, at 3 hertz, it should be 2, and it is indeed 2. Then the next frequency, I don't know why I am getting this at 4 hertz. So this is some of a error. So this is inaccuracy which is coming up in DFT. Then I have another which is at 10 hertz. I should have 1.5. So at 10 hertz it is indeed 1.5. And what else? So F3 was, and F4 was 16, and I get some peak at 16. It should be 3.5, but I get totally off. It is giving me 7, and because sampling frequency is 32, it cannot give any values more than 16 hertz because of that Nyquist limit. So I don't get results beyond 16 hertz. So what does that mean? That maybe I can still keep the duration same, 3 seconds, but I have to increase this sampling frequency, and let's see. So my sampling frequency, what I did was I made it 64 hertz. So I doubled it. So once I double it, theoretically I will get all the frequencies up to 32 hertz. And what we see is, first frequency is at 1, amplitude 1, which is good. Second frequency is at 3 and amplitude is 2, which is good. Third frequency is at 10 hertz, amplitude is 1.5, which is good. Fourth frequency is at 16 hertz, amplitude is 3.5, again, which is good. Fifth frequency is 17 hertz and amplitude is 7, which is good. But then you look at the next frequency and you get something around 28 or 27, and its amplitude is also 11. Okay? So you are getting good results at this. And then you do at 128 and you get probably even more accurate results. So the point what I am trying to make is that if you have your sampling frequency just at Fs, that will give you results till Fs over 2, but that does not guarantee that the results in the neighborhood of Fs over 2 will be precise and exact. So even though theoretically you will get some value at Fs over 2, but its value may not be good enough. So you have to increase. So because this is what we see, here Fs was 32 and I am getting some spurious result at 16 hertz. At 16 hertz I am not getting anything, and some spurious result I am getting which has an amplitude of 7. Okay. So ideally I should have gotten at 16 hertz the amplitude should have been 3.5, but I am not getting that. So what that tells me is that even though I am getting data, see I am getting data till 16 hertz, but that does not mean that that data in the neighborhood of Fs over 2 will be accurate enough. That is the moral of the story. So a couple of important points about these two things which we discussed, that if I have to have my duration reasonably long, and if the duration is not reasonably long, and if I expect some frequencies, some low frequencies to be present in my signal, which means that their time period is large, and if the duration is not large, then I may not get accurate results, because I need to have at least 1 or 2 cycles of that low frequency information to be completed, and if my duration is not large enough, time duration, then the results at low frequency end may not be good. This is the first thing. Second thing is, if we don't want low frequency components, they may be that maybe we are interested only in frequency, let's say from 30 hertz to 5000 hertz, and we are not interested in any information below 30 hertz. It could be a situation, let's say. In that case, and we also don't want to have very long durations of signals, because it takes more processing time. So in that case, what we should do is we should use these filters, high pass filters, to eliminate the signal from all low frequency information, and then we subject it to DFT. Okay. So that low frequency information is gone, and that will not corrupt our results, it will not create confusion for our results, and then we just use information to then we use the DFT. The second point is, for the high frequency end, to ensure that we get information of high frequency end, we have to first definitely ensure that our Nyquist criteria is satisfied, but then we should not limit itself to Nyquist criteria, but we should go, our sampling frequency should be maybe 3-4 times more than the Nyquist criteria, and then we will get reasonably okay information about high frequency content. Similar also, if in the high frequency range, we are not interested in, say, some super high frequency information, then then what we can do is that we can acquire the signal and eliminate the high frequency content using low pass filters, and then do the FFT of that. So that is another interpretation of it. And the last point I wanted to discuss was about frequency resolution. Frequency resolution. So whenever you do a DFT, on the x axis you plot frequency, on the y axis you plot xk, right? And then you have different points. The spacing between these 2 points is called frequency resolution. Okay, or delta f. Let us compute this. So we know that frequency is equal to k times fs over n, right? So if this frequency is f1, this frequency is f2, then f2 minus f1, or I can make it more general, fk. So this is fk, and this is Fk plus 1, then Fk plus 1 minus Fk is the resolution delta F, Fs over n k plus 1 minus k. I am just using this relation for this thing. So, this is nothing but Fs over n, okay? Or I can express this as 1 over n over Fs. Now, n is the number of points, right, total number of points which we are considering for our analysis. Fs is the sampling frequency. So, n over Fs is nothing but duration of time signal is equal to t, right. So, this is equal to 1 over t. So, what does that mean? That if I acquire data for 1 second, my frequency resolution will be 1 hertz. If I acquire data for 2 seconds, my frequency resolution will be 1 over 2, half hertz. If I acquire resolution for 3 seconds, my frequency resolution is going to be 1/3 hertz, and so on and so forth. If I acquire data for half a second, my frequency resolution will be 2 hertz. So, if I narrow the duration of my data acquisition, the frequency interval in the frequency domain will become larger. If I acquire data for more period of time, my frequency interval becomes smaller. So, that actually also tells us that at low frequency we want finer frequency resolution, because we have to go from 1 hertz, 2 hertz. See, between 1 and 1.3 there is a 1 and 1.3 hertz, there is a 30% difference. If the same difference is at 1000 hertz, 1000 and 1000.3, that difference is negligible. So, if I need more accuracy at low frequencies, I have to increase the duration of the signal. So, this is again something we discussed earlier, but it also flows from this information. So, this is the last point which I wanted to cover in today's lecture, and I once again thank you for listening patiently to all this discussion, and we will continue this discussion in the next class as well. Thank you.